Enrico got his, or did his graduate work at Cambridge under the supervision of Ramirez-Ruiz. After that, he moved to the Institute for Advanced Study, where he was a 5-year member and a Chandler Fellow. Following that, he moved to University of Santa Cruz, where he's been a member of the faculty for several years now. And he's an expert in high energy astrophysics with a particular emphasis on GRBs and other transient phenomena. And today he's going to tell us about some of his work on tidal disruptions.
Thank you. I'd like to thank Shane and Phil for inviting me here. At some point I may ask him to turn the mic. Sure. I'm going to show you something. Okay, so I'm going to talk about tidal disruptions of stars by massive black holes. But really, I want to first motivate the talk, and I'm really going to talk, or the motivation of the talk is really to unveil that many placements, and I'll let you know what I mean by that. Okay, before I proceed, I just want to talk about my collaborators. A lot of the work that I'm going to show has been actually performed by my grad student, James P. Duchamp, who's at UC Santa Cruz, and some of the work has also been done in collaboration with Stefan Roswell, which is at Bremen, and Dan Casey at UC Berkeley. Okay, so the motivation of the talk, so that you get a little bit what we're thinking was when we started thinking about these new aspects of tidal disruption, is really to try to understand the population of dead black holes in the local universe, and we'll try to answer these questions. Does every galaxy hold a supermassive black hole at its center? And what I'm going to try to argue is that most of the current signatures that we use to infer the presence of supermassive black holes are in fact biased towards the more massive counterparts, which of course are the minority once you believe the mass function of black holes. So the signatures are of course gas and stellar kinematics, as you can tell from here, in which we try to infer kinematically what's the mass of the black hole, and as you can see, this measurement gets progressively more difficult as the velocity gets smaller. And even though people like Marla have tried to make some heroic efforts in measuring velocity dispersions in these dwarf galaxies, it's very hard to really constrain black hole masses below about 10 to the 6th. So this method works relatively well for supermassive black holes. I wanted to have like an interlude just to make the point that in recent years there's been some claims for a mass concentration in the centers of globular clusters, which in some cases are associated with the presence of an intermediate mass black hole, like in the case of M15 of G1. There's some debate whether omega Cen is at all or not a globular cluster. And what I just want to say is that this is tentative evidence, and in fact there's a huge amount of debate because the presence of the black hole in some cases is not actually necessary to explain the exit velocity dispersion. It has to do a lot with where you define your centroid in the certain brightness profile and so forth. But this is certainly an interesting prospect to really find this intermediate mass black holes, and of course the fact that we follow the M-sigma relationship, in fact, as a globular cluster should actually make you more concerned. Yeah.
These are margins and just like
yeah, so for example in G1 there's been a lot of, this is a paper by Noyola and collaborators, and in this case people have shown that if you keep the center of the surface brightness slightly in a different place, then you don't actually require the presence of the black hole. So it's rather controversial and it's a difficult measure. But if they're there, all of what I'm going to tell you is actually really exciting, because you're going to have a lot of these stars running around the black hole. Another way of measuring or inferring the presence of this black hole is of course by the digestion of matter. And as you know, the digestion of matter is limited by the Eddington limit, which is the balance between radiation pressure and gravity. That's of course mass dependent, so of course that's again biased towards the more massive counterparts, which of course you can see them from farther away. This is some of the histograms by Jenny Green, and as you can see, once you go to low analysis, it's actually very, very difficult to start putting constraints on the presence of these objects. Now, moreover, since you're ultimately constrained by the mass of the black hole when you get to the limit, you can only constrain the presence of these intermediate mass black hole locally, and the problem is that locally a lot of these black holes are in fact a star of gas. Yeah. So very unlucky because most supermassive black holes at redshift 0 are in fact inactive. And I like this diagram that I just found that I think nicely illustrates how little we really understand the mass function of black holes at low mass n. So what we can try to do here is, of course, come from the luminosity function of stars and try to infer if they really follow the MC relation, what will be the black hole demographics of this. But something that I really want you to focus your attention, this is the mass function inferred by Green and Hope for active local AGNs, and of course there's a factor of 170 in the fact that those that are actually inactive are certainly much more common in terms of number density. And the key is whether or not you believe extrapolation here, which is very, very uncertain. If the extrapolation continues, you will be interested that some of these objects could actually pose massive black holes that are more intermediate mass more intermediate mass. So really your motivation was, well, can we come up with signatures that can really unveil these inactive populations locally? Just to give you a feeling of some demographics of black hole in our local universe, if you look up to Virgo, say about a sphere of about 20 megaparsecs, you realize there's about 200 of some massive galaxies. So there's lots of these dwarf ellipticals, 50 or 80% that are thought to be nucleated and are thought to be potentially containing a massive black hole in the interior. And as you can see, the number of these black holes, even in the local universe, is really abundant. The problem is we don't really see that the majority of them are in fact inactive. And the demographic is done by Macquarie and Tidal. Okay, so the black holes are speculated to be there, and we really thought, well, can we find an observational signature that is in fact not biased toward this supermassive black hole does? And for 2 decades, since Ramirez-Ruiz wrote this very nice paper in Nature, it's been proposed that tidal disruption of stars really can offer a probe of these coalescent black holes. Now, most of the previous discussions in this field has really focused their attention in signatures associated to the digestion of the stellar debris. Okay? When a star actually gets disrupted, as I will show you, about half of the mass is bound to the black hole, comes back, forms an agro-elemental distribution shock, forms a disk, and feeds the black hole. And of course, that is again constrained by the ending of luminosity. And of course, it's again biased towards the more massive counterpart. So what I'm going to try to discuss today is a series of what we think are novel signatures of tidal disruption that are in fact biased towards low mass black holes. The signatures are in fact stronger for lower mass black holes, and in some cases they certainly overwhelm the digestion of the green luminosity that we expect. Okay, so I sort of given you the motivation of why we want to do this. And if you're interested, as I will tell you a little bit more, in the digestion of the debris, we can talk more offline. So what I'm going to try to motivate in this talk is really the physics of tidal disruption. And I'm going to focus on ultra-close passages. So stars that penetrate deep beyond the tidal basis, and I'll explain what the tidal basis is. And I'm going to focus on 2 signatures, tidal shock breakouts from main sequence stars, sun-like stars. And then I'll talk about this exciting possibility of tidal disruption and actually ignition of black holes. Okay, so when tidal fields are weak, like that in the Earth, the sort of height of the ocean compared to the size of the radius of the Earth only changed by 1 part in a million, and because the change is so small, you can actually assume that the tidal field or the tidal force is actually constant. However, when the tidal forces increases, the response of the surface is highly nonlinear. Yeah? And you no longer can assume that the tidal force is constant across the object. And even though mathematical solutions, very elegant mathematical solutions exist, for example, this is the classical Kress and Minkowski, in which you measure the energy deposit in the oscillations for a parabolic orbit, which you decompose the tidal field into spherical harmonics. Some of these, of course, break down when the scale of the perturbations becomes comparable to the size of the object or the size of the fraction of the object. Okay? So therefore, we resort, and more of what I'm going to talk about, is how we are tackling these problems numerically. And hopefully I will demonstrate that our solutions actually converge to the classical classical formula. So I'm going to use two different approaches, or a group has been using two different approaches. One is a Lagrangian method, SPH method. This is very, very effective if you really want to follow what happens to the debris after the tidal disruption, because it allows you to, the star to grow in size. As you know, the size of the tidal radius compared to the size of the orbit, or if you want, as I will show you, the orbit of the most bound material compared to the tidal radius is very extended, and the Lagrangian methods really allow you to follow the debris of the star. And then I'm going to talk about an Illyrian method, AMR method, in which, of course, in this case, we do the calculation in the center of mass of the star. The star is basically forced to be in the box. So in this case, this arrow is basically showing you the position of the black hole relative to where it is in the box. And this, as I will show you, it's a really good method to actually look for shocks. I'll show you these very deep compressions. Okay, so the stars in the vicinities of black holes have complicated orbits because they're affected by other stars and the black hole itself. And in the random walking angular momentum, there's a non-negligible probability that interactions with other stars send one of these stars in a radial Mohs cone orbit, in which it gets close to a black, so close to the black hole that the tidal force becomes comparable with the self-binding energy of the star. So initially, and these orbits are almost parabolic because most of the stars are scattering the sphere of influence. And as I will show you, that's much far away than tidal radius. So a star can be, or the orbit of the star can be treated the approximation of the star being a point mass, but of course once it gets too close to the black hole to suffer tidal deformations or even complete disruption, the point mass approximation of course breaks down. So what happens? The radius here I just showed for a 10 to the 6 solar mass black hole. This is the Schwarzschild radius. The tidal radius is given by this formula, and it's simply understood as if you take a virtual sphere around the black hole, what is the radius in which the average density of the mass that you're basically stretching in the virtual sphere is comparable to the density of the star. As you know, tidal forces depend on the gradient of the force and goes 1 over r squared. So what matters is, it's the density, the average density of the star, and the ability of the black hole to affect the structure of the star depends on that ratio. Okay, so beta equal 1, here I define beta, the ratio of the pericentric distance to the tidal radius, such that if beta is a very large number, it means that the star is penetrating much deeper into the potential of the black hole. So what happens? Well, as the star falls to the tidal radius, it develops a quadrupole distortion whose amplitude attains a order unity at the tidal radius. The gravitational torque spins up the star to a sizable fraction of its co-rotational angular velocity, and it's both the tidal Boltzmann distortion of order unity and the large surface velocities that basically conspire to break apart the star. Where does the energy come from? Well, the energy at pericenter, the kinetic energy of the orbit at pericenter is higher than the binding energy of the star by the ratio of the masses to the 2/3 power. So if you have a million solar mass black hole, the kinetic energy of the star at pericenter is 10,000 times larger than the binding energy of the star. So that's the energy reservoir that you're tapping to break apart the star. Okay, so just to give you a feeling of how often this happens, of course the black hole dominates the dynamics very simply when the velocity is larger than the velocity dispersion. That nicely defines a sphere of influence that contains an integrated number of stars similar to the mass of the black hole in which it dominates the orbit, or 10 to the 6 solar mass is about r set, which is what we see in the overlapping center. And the frequency of interaction just simply depends on the number density, the area, and the velocity. And here I show the cross-section, and of course for these interactions, if you're penetrating very deep, the gravitational focus term dominates, and therefore that allows you to drive the frequency of interaction, and if you believe in the m-sigma relationship, that allows, for example, one invariant to derive the frequency of interaction as a function of the black hole and the penetration factor of the how deep you penetrate. So So of course, the deeper you want to go into the tidal field of the black hole, the less frequent this is. And then you also have to be worried that depending on the mass of the black hole, the tidal radius and the Schwarzschild radius may be equal. As I will show you for white dwarfs, if you throw a white dwarf into the galactic center, yes, it will get disrupted, but inside the event horizon, and you won't see it. Yeah? So these are thought to be rather optimistic rates, but just to give you a feeling, one of these stars is scattered inwards into an orbit in which it approaches the black hole dangerously close, like once every, a few thousand years, maybe once every 10,000 years. Okay, something that's interesting is that the tidal radius is defined as, by the average density of the star. But for example, if you take a solar type star, there's a huge density gradient between the interior and the envelope. Okay? So what ends up happening is actually the core survives. You have some material that is actually bound, some material that is unbound, but actually the core survives. So you have to go deeper than the tidal radius to have complete disruption of the star. Okay, so this is a simulation of actually not a star, but a planet with an N equal 1 polytrope, approaching of state. And as you can see here, the envelope is significantly shattered at the tidal radius, but the core survives. Okay, so just to give you a feeling of how well we're doing in trying to simulate this event. So this is the Press-Antokovsky energy deposition prediction as a function of how close you're getting from the star. And what I showed here are the various simulations that we're performing. So the first things that I want you to notice is, the majority of the energy in this case is carried by the L equal 2 plus or minus N equal plus or minus 2. The quadrupole distortion, particularly for stars, carry almost 90% of the energy. Of course, that depends on how close you get. So we're certainly getting the predictions right compared to the Press-Antokovsky for the L equal 2 formalism, and we can resolve it. We can resolve the L equal 3 rather well. The first thing to notice is that at some point our simulations are flat, so we're basically predicting the same amount of energy deposition irrespective of how close we get, and that's of course a resolution limitation. Why? Because what is happening if you get farther away than the black hole, you're not resolving, the delta R over R, the distortions in the stars. They're smaller than the size of your grid, so of course you're over predicting the energy deposition. Yeah. So here we're basically resolution limited, and we now have got more supercomputer time, and we're really able to get within 10% of Press-Antokovsky, which not necessarily has to be the correct answer. But it certainly is giving us confidence of what we're doing. It's certainly accurate. Okay, so the nice thing about trying to do this numerically is you can expand into the regime in which the reaction of the distortion becomes nonlinear. Okay? So what I'm plotting in this is sort of a zoomed view of this part of the diagram. And what I'm plotting here is the energy, the orbital energy, the resultant energy, orbital energy as a function of the initial orbital energy. Yeah. So naively, what you always think, and as I explained to you, the star goes in and basically transforms a fraction of its kinetic energy into oscillations. Yeah? And naively you expect, well, the star is actually going to get bound to the black hole if it was to survive. Yeah? And you go from a parabolic orbit to basically a bound orbit. Now, what I'm showing you here is that this certainly happens, this is when the two are comparable. This certainly happens for relatively deep penetrating impacts, but there's a region here in actually that those oscillations lead to the star actually getting unbound to the black hole. Yeah? So then the argument is, or the question is, why that's the case? Well, the reason is that in fact mass ejection in the two destroying blowups is not symmetric. Yeah? So if you eject, basically the tidal field is not perfectly symmetric, and there's a difference in the mass ejected, and therefore that gives a kick into the star. And the kick actually moves from parabolic orbit to a hyperbolic orbit, and that basically reduces your effective cross-section of capturing these objects. And And of course that, as you know, depends very strongly on the mass ratio, because that tells you, how symmetric the tidal force is. And as the mass ratio increases, we find that this effect becomes less and less important. But for example, for a Jupiter-like interaction, then it becomes, rather important, because the mass ratios are small.
There's a point on the y-axis here.
Sorry?
There's a point on the y-axis.
Yes?
No, to the left.
Oh, okay. Yeah, I think this is this would be an ideal problem. I made the plot this morning.
Well, let me also ask you a question about it. If this is the AY result,
Yes.
so how many grid cells do you have around your star?
So we try to keep so we have about 500 per length scale. In the ones that I'm going to show you for some of the mains, for the very deep penetrating campus, we get to have 800. But that really takes like a few months. And we do maybe 6 credits. Okay, so what I'm going to show you here is basically what happens to the sun-like star that approaches, it's the tidal radius on a black hole that is basically the same mass as our galactic center. So 3 times 10 to the 6. So you can see this is time. As you can see, the star is, in this case, the black hole is coming towards the star and then moving away. You get this quadruple distortion rates of amplitude of order unity. The core survives. The core is actually rotating rather rapidly, and it sends these spiral shocks, which are ultimately constantly heating the envelope of the resultant star. And as you can see, something that starts with the size of the sun, it becomes a rather extended object. Yeah? And constantly, as the object moves away from the black hole, these tidal long-tail features are constantly falling into the interior of the star and are producing these spiral shocks that are constantly heating the envelope. I'm not going to talk too much about it, but I just wanted to mention. So, we talked about, I call this process phase lifting of stars. You can take a star and make it look much younger than it actually is, because you have deposited significant amount of energy in the envelope, and the key is what's the Kelvin-Helmholtz timescale of the envelope, for how long, what will be the diffusion timescale for that energy to leak out, and whether or not these stars will appear to be much more massive than they actually are for the Kelvin-Helmholtz timescale. So we call this quasars, and as you can see, they can get to sizes that are comparable to the class B stars, and what we have found is that maybe you can mimic some of the surface gravity measurements, just because these objects are rotating, very close to breakout.
You're not doing nuclear reactions.
No, so here we just, this is basically a simple, we modified MESA to do the calculations, and basically this is just a diffusion calculation. And as you can see, the luminosity of the star is rather high, it's 100 times solar, but then very rapidly decreases and goes to the main sequence. So the key is, if in a snapshot of the galactic center, how many stars I want to see, you take the rate and multiply by the lifetime of this object, and what we find is that maybe one star, if not a few, maybe these space-lifted stars, but of course you cannot explain the population of massive stars. Not all massive stars have to be phase-lifted, and what we're trying to work hard is trying to really see what the atmospheric characteristics of these space-lifted stars. But I just wanted to mention that in this case, when you go just at the tidal radius, the star usually survives. Yeah? And then there's a non-negligible probability that the star will not return back to pericenter because it will get scattered by the sphere, the star within the sphere. Okay, so as you go deeper into the tidal radius, the first thing that you should notice is that the semi-major axis of the star doesn't have time to basically align with the direction of the black hole. And that makes sense because naively you expect that the tidal radius, the rotational angular velocity, is comparable to the time that it takes to pass. That's why the fundamental frequency is highly excited, because the time scale of interaction is comparable to the fundamental frequency of oscillation. We find that once you get to beta of 3, the star is completely disrupted, even the core, and then you get about half the mass is bound, half of the mass is unbound, and the center of mass of the orbit moves close to the parabolic orbit as you expect. So, and of course, the force, is it's no longer oriented in the major axis, and that creates, of course, torques that are starting to be rather bigger. As you penetrate deeper, as I'm going to show you in a beta of 7 case, the elongation of the star almost happened close to the vector line of the motion of the center of mass. Yeah? So the star is no longer able to very rapidly rotate as it penetrates deeper. Now, as you know, these objects get sort of banana-shaped distortions, but what we were more interested in was not what happens in the orbital plane, but what happens perpendicular to the orbital plane. Okay? So you have 3 major tidal axes. In the orbital plane, basically you have this very large surface velocity that basically can combat compression. The perpendicular to the orbital plane, you get huge compression. So how do you think about this? Well, once the star crosses the tidal radius, you can think of it as the pressure of the star becomes irrelevant. And its evolution behaves almost like a set of collision with sparks. Yeah? So perpendicular to the plane, basically it starts collapsing, and in fact, if it behaves as a set of collision with particles, they will all cross, in a plane at the same time. But of course, the pressure increases, and the pressure actually bounces these strong compression. And I will show you some effects of this. But the star can get significantly compressed in the orbital plane, and this is what we were interested to see, how these compressions. Okay, so some of the observational signatures that have been discussed are, of course, the gravitational waves, which are hard to see because they're just a burst. Then I'm going to talk about the shock breakout signature, which basically takes place after a few tenths of seconds. Then you, of course, have half of the material is bound, half of the material is unbound. There's the possibility, since the material starts from a higher adiabat, as I will show you from the shock, as it cools down and it gets close to the photosphere, you actually get a hydrogen recombination transient after a day. That if the black hole is relatively low mass, it can in fact outshine the total optical luminosity just from the foldback, which basically, in the case of a black hole of 10 to the 6, the foldback proceeds in timescales of weeks. Yeah. The return of the most bound material for a 10 to the 6 solar mass black hole is of the order of a few weeks. And you, of course, have to circularize that material, and then the viscous timescale there will be fairly quick. And then some people even talk about the reprocessed foldback radiation. Yeah. That will be the radiation from the foldback accretion basically illuminating the outbound retinal. And of course, that decreases depending on the cross-section sustained on this object in the sky. Okay, so what I'm going to talk about is the simulation just to motivate these shock breakout calculations. So here we use black hole of 10 to the 6 solar masses, a beta of 7. We use a purely hydrogen fluid. The star profile is set by Na equals 3 polytrope, but the gas reacts as a gamma 5/3. And the maximum resolution that we have here is to ask no question is about 2,000 kilometers. And just to compare with other calculations, so there's a very nice paper actually by Bassar and Luminet in which they assume that the whole star collapses in one dimension. Yeah? And they follow the collapse in one dimension. Here they're assuming there's no commutation. These guys have probably factor of 10 better linear resolution in 1D. And the SPH calculations will basically do a factor of 10 not 50 in linear resolution in these deep penetrating cavities. Yeah? And of course, we need really high linear resolution because these large pressure gradients, as I will show you, will precede the shock formation, and we really want to have high resolution too. Okay, so this is a simulation. Again, we made, we put here the black hole, the Schwarzschild radius, just to give you a feeling. And I showed you the trajectory of the black hole with respect to our grid. But of course, we're trying to do everything in the center of mass of the star. So of course, the black hole, with respect to the box, the black hole basically changes direction. And as you can see, the distortions are not completely symmetrical, and it leads to the star being sort of elongated in these banana shapes. Now, this is, of course, very interesting, but as I was emphasizing, what is extremely interesting is what happens perpendicular to the overall plane. And what you get is these very, very thin pancakes, yeah, of compression and pericenter. So I just wanted to give you a few time scales to guide your physical intuition what's happening. So just to give you a feeling, this is basically the initial distribution of the star, and this is at pericenter happening. Yeah, so it's of course highly, highly deformed and very strong compression in the orbital plane. Okay, you can calculate what are the bulk motions of the distortion just by calculating what the radius of the star comparable by the velocity at pericenter, and that's about 10 seconds. Yeah, that's about the time scale that it takes for the interaction. And then you can calculate, that the velocities are a fraction of c, yeah, 10 to the 10 centimeters per second. That's comparable to, if you want to think about it, the orbital velocity. Yeah. And then the interesting thing is that the star can only react, on a sound-causing time scale, which is about 10 to the 8 centimeters. So what I want to guide your intuition is that this compression is actually supersonic. Yeah? And those pressure gradients are going to steep into a shock. Okay. So what happens? This has been very nicely illustrated by Carden in '83 using a model that I can go into more detail if you're interested. It's called the affine model. It assumes basically that the object always behaves like an ellipsoid, and there's basically no mass loss in that case. So as the star basically compresses, okay, you start building these very, very strong pressure gradients. But of course, as you go into your minimum approach distance, the tidal field is always growing. So pressure can basically not overturn that pressure. So this basically increasing pressure is counterbalanced by the tidal pressure, if you want to think about it, which until shortly after the star reaches pericenter, the tidal field starts to decrease. Okay? And that allows the pressure buildup to actually overturn the collapse. And you see these nicely in this toy model, in which basically the tidal field goes to very, very small values. Why? Because the tidal component depends on the z component. And then the pressure is allowed to build up. You're leaving the object, so this R is increasing, and then you overturn that pressure balance. And self-gravity is really not important. So the vertical stance of the star continues to shrink until the tidal field has reached its maximum value, and then the pressure can actually overturn that collapse. So let me show you how this looks. So just so you realize, I'm multiplying this by a factor of 100 so that you see the collapse. The black hole is here, and then you're sweeping, the most, the largest tidal pressure across the star. So what I'm showing you is a cut through the major axis, and as you can see, they're coordinated so that you get a feeling of where the black hole is as the compression goes around the star. And what you immediately see is that the core, of course, is less vulnerable to that compression because the sound speed is much higher than that. Yeah, you have a higher pressure. Okay, so I'm showing you here the temperature, which for betas of 7 actually increased significantly the virial temperature of the star because the compression is no longer, the compression is actually just purely driven by the gravitational potential of the black hole. Yeah, the pressure in fact is becoming low. So something that we noticed, which we're interested in, is that we have two shocks. We have the leading edge and the outer edge component, in which those pressure gradients steepen into shocks much easier than in the core, which is of course much more resistant to tidal to compression, just because the sound speed here is of course much higher. So as you can see, the formation of the two shocks before the bounce, yeah, and then the bounce is very dramatic. I'll show you my diagram of how I view these components. So this is the diagram that we use to try to understand it. So we're looking at a section of the star. I'm indicating these arrows as the tidal field. So as you can see, the tidal field gets stronger. Yeah. The collapse, the star is basically changing the height of the star. At some point, you start moving away from maximum compression. The pressures, build up is enough to actually overturn the flow, and you form a shock at the tidal field, and then you get a rebound. And the star starts to expand. Here you have the photosphere, as basically expand, the background expands. So when you're trying to understand shock breakout, say for example in supernovae, you always assume that the background profile is static. Here you're basically in a background profile that is expanding in the value. So the key issue is that the maximum luminosity actually is when the diffusion time scale is comparable to the expansion. So what do I say? Well, that the energy output is controlled by a balance between photon diffusion and adiabatic expansion. And what we find is, even though naively you think that most of the photons are going to leak at the tau equal 1 photosphere, that's not the case, because the expansion actually allows you to have things as deep as 1,000 or so tau, and this is basically when the maximum of brightness takes place, when the expansion and the diffusion are comparable. Okay, so in order to calculate the light curve, I want to say a few things. Of course, first is that we're using an adiabatic equation of state, and second, we're now resolving the atmosphere. So what's going to happen is that this shock is going to transition from being gas pressure dominated to radiation pressure dominated. And it's very important for us to actually describe, what the conditions of the atmosphere is. So what we do is we stitch basically the conditions that we have at, where we believe our resolution is rather adequate, and we stitch an atmosphere model, which we assume is actually collapsing in a cell-similar fashion, to solve basically the eigenvalue problems at each radial extent of the star.
What fraction of the mass gets shocked?
I would say maybe 5%.
The other on both.
Yeah, now, of course, if you just calculate the thermal energy content divided by the time scale, you expect that these shock breakouts should be very, very limited. But in fact, what this adiabatic expansion tells you is that it quenches a lot of the energy, and the peak values are not as high as we want. So this is the X-ray luminosity as a function of time. The total volumetric energy that you get is about 2 times 10 to the 43, which is a very small fraction of the total thermal energy content of the star. But what we were excited is that you do certainly see this two-peak feature. And the nice thing is if you're able to measure this and if you know the delay, say combined to other signatures, you can get either the mass of the black hole or the radial extent of the star. You have a mass radius relationship. So the time difference between these two peaks is of the order of a minute, which is the compression in the leading edge and the outer edge. And of course here we're assuming that protons and electrons thermalize effectively and that you're getting a black body, which may not be the case. You may get a strong non-thermal component. And, there's a lot of really nice work being done in supernova shock breakout that it shows that not necessarily you actually are thermalizing effectively the particles. In this case, this problem is a little bit more difficult because you're in an expanding background.
So the shock that is coming out, this is roughly a planar shock or cylindrical shock?
It's almost a planar shock.
Almost a planar.
Although we do find that there's some lateral communication of the star. So this idea of treating the whole collapse as one peak sort of misses the future.
Right. So and then what's the velocity of the expenditure? Is it basically 10 centimeters per second, or is it much slower than that? You're getting a lot of energy from the peak as well. You kind of understand that. Why do you need the tau? I'm getting out that tau.
Yeah, because the expansion of the background is very, very rapid.
I see.
Does the double peak, does it persist for different beta?
Yes. So I realize that anyway. So you need basically a wild field of view instrument with a good resolution between 1 and 10 energy range, and exists because the perfect mission no longer exists. But something along those lines will be perfect to try to find things. For example, you expect like about 1 tidal disruption event optimistically from the Virgo cluster, survey of the Virgo cluster, which should certainly lead to these shock breakouts. Yeah, so just to answer your question, this is basically our prediction for where the shock breakout in terms of mass is more prominent. And basically what happens is that the lower the mass of the black hole, the larger, the larger your effective beta is. And actually, the deeper you penetrate, the brighter the luminosity that you get in some ways. And here, the thing is cut off because we assume the one and very idea that below 10 to the 4, a lot of these dwarf galaxies are no longer nucleated and are thought not to have black holes. Or if they have black holes, there's not a large number density of stars. But yeah, we can talk about that. If you start penetrating deeper, as I will show you, basically for orbital, the orbital that we have assumed is no longer the case because the orbits in D are very different from parabolic. Okay, so for the second part of my talk, I wanted to talk about, well, now what happens if you actually take a white dwarf and you make it penetrate deep? And we started thinking about this because, of course, if there's a shock and you raise the density to a higher adiabat, there is the possibility of having emission. So for white dwarfs, it's a little bit more complicated in terms of the available parameter space that you can have. So one problem is, of course, when the tidal radius is equal to the partial radius. That means that the average density around these black holes is smaller than the average density of a white dwarf, so they get disrupted inside the event horizon and you're not going to see it. So during the regime here, the white dwarf enters the black hole, but you can also be in the regime the black hole enters the white dwarf in the sense that the Schwarzschild radius becomes comparable to the size of the object, and here not doing full GR calculations, making this problem. But there's a maximum beta in which you can penetrate that it could be, pretty high for low mass white dwarfs, because of course they're easier to disrupt and more difficult to higher mass white dwarfs. And as you can see here, that for lower mass black holes, you may be able to disrupt, and as I will show you, ignite it even for a black hole that is about 10 to the 5. Okay, so what I'm showing here is a 0.2 pure helium white dwarf. Of course, nature or stellar evolution doesn't make those. You have to make them by other means. But it was just an example of whether or not the lowest density white dwarf that we can feel actually ignited. We use an intermediate mass black hole of about 1,000 solar masses at a beta of 7. Here we use an SPH method, and we use a realistic equation of state and a 7 nuclear species on our network because we wanted to get the energy deposition by the nuclear reactions. Again, a lot of what I have told you is very similar. You get these distortions in the orbital plane, this elongation. This elongation, as you can see, becomes much less symmetric. Why? Because the mass ratio here is much smaller. And you get, I'm showing the temperature and density. So it's highly compressed, but severely extended in a flow-like shape. But what is important is what happened in the orbital plane. Because the structures here are so thin, I decided to plot just the surface density, not a density in the top plane. And what is interesting is whether or not the densities and temperatures are high enough that you can actually. Just to give you a feeling, you immediately are going to, we have actually now done this with AMR, and we get similar conditions. SPH has a little bit of difficulty, much more difficulty resolving these pressure gradients. To give you a feeling of how different this problem is, remember for a sun-like star, it takes about 10 seconds to cross. Here it takes about 0.18 seconds. And the ability for the thermal time scale is of course much longer. So again, this compression is highly supersonic, and these pressure gradients basically steepen into a shock. If you actually follow the adiabatic compression and calculate triple alpha and the dynamical time scale, you don't get explosion. It's only when the shock actually moves into a higher adiabatic. So the development of a shock is crucial in trying to understand this ignition. So what I'm showing you here are the trajectories of 3 simulations, representative of runs. Of course, the 0.6 and 1.2 are carbon oxygen, and the 0.2 is the pure helium. And here is just the boundary where the burning time scale is smaller than the dynamical time scale, or the reactive time of this time. So what happens? Well, you're in a moving background. So if you start triggering energy generation by nuclear reactions and they're too slow, the fact that you're stretching will quench the burning. So what you really want is the triple alpha reaction to be much faster than the dynamical time scale, so you can trigger the ignition. And in these cases, we're certainly comfortably in that regime. And what we get is that a large fraction of iron group elements are sensitized. The exact development of the shock I want to point out depends, for example, there's a nice example here of a 0.6 carbon oxygen white dwarf, same penetration parameter, but in one case we use a Newtonian potential, and the other one we use a Paczynski beta potential. And as you can see, there's some difference in the amount of nuclei that we produce. Yeah? So now we're basically expanding to do at least a fixed metric GR calculation of this compression. And I will show you there's some interesting. But for deep penetrating encounters, we can actually produce a significant amount of metal.
So how do we get these compared between AMR and SPA?
Well, you kind of know the answer, but the SPA sort of gives you higher entropies than the AMR just because the viscous dissipation. But yeah, in the AMR concept, so we have done this problem in 3 different ways. We have done it in the AMR, not triggering any nuclear reactions, and then just follow the rho and T trajectories on a full network, and that more or less gives us about the same results. We have actually put a 7, 13, and 19 alpha network, and more or less we're converging, but it does strongly depend on resolution, which of course the AMR viscosity or energy, this artificial energy dissipation depends on the resolution. And then we have done this in 1D, in which we assume that the wire will just collapse, and in that case we really get a detonation. But even in 1D, you're not even resolving this scale of the okay, so this is, of course, it gives you a very nice segregated element abundance because they trade the density. You have an iron core, carbon, helium, silicon. This is for the 0.2 solar mass molecule. What is interesting here is that a significant fraction of the energy goes into unbounded material. And I will show you that. So if you look at the distribution without burning, you get about half the mass is bound, half of the mass is basically unbound. And with energy generation, you get maybe like 70-30%. Because basically that energy input allows more mass to actually be unbound. And it moves significantly, I mean, it moves very, very fast. A fraction of the speed of light. So these are, sorry. This is energy per particle, and of course, if it's negative, it means that it's bound, and it's positive, it means that it's unbound. So then you get a feeling that a large fraction of these sensitized elements are in fact unbound, and are moving a very large fraction of this. So this calculation is one that you don't get nuclear ignition, but since you don't get nuclear ignition, actually 95% of the calculation is just in the maximum compression phase when you have a nuclear network. But what I wanted to illustrate here is basically the shape of the unbound debris. So here's a black hole, and as you can see, in this case, about half of the material is bound, half of the material holds out, and you get these. And this is what I really wanted to focus on. That of course the material is spread. It's very, very thin material, very rapidly expanding. So you immediately think, oh well, I have about a sizable fraction of nickel. How is the light going to look like? In typical Taiwanese and spherical Taiwanese, of course, everything is dictated by the diffusion time scale. But here, the diffusion time scale is different depending on what direction. You can actually diffuse perpendicular to the orbital plane.
Is there burning happening in this interface?
No. So this is just no burning. We turn on it's a 0.6 solar mass. Yeah. No, you never get burning in the UV. We find, for example, that maybe in a common envelope evolution phase, when you have a neutron star, there you may get some hydrogen burning, but that's the only phase that, or some of the work that Brian has done, like the white dwarf, neutron star. So at those densities, you get something you can.
Well, I talked to him about this actually. This is interesting. He was here recently. There's some interesting results on this stuff.
Yeah, I would love to hear about it. Okay, so the mass fraction that is ejected, although it's less spectacular than at 518, although I actually think that this channel is pretty spectacular, has very distinct observational signatures. One is that it should be seen in association with a dwarf galaxy or a star cluster. The generate star should be on average lighter, and the lighter should be rather unique as a result of both the material being squeezed and moving very fast. And the ejected debris is expelled with very large velocity. So the way to think about it is in the frame of the star, you get a typical explosion, but the center of mass is moving so rapidly that either if this material is moving towards you or away from you, you will see strong velocity shifts in the light. But I'll show you how the light is working. So this is our mapped 0.6 solar mass white dwarf. This is basically all the material that has a positive specific binding energy. This is the iron, and this is basically some cut intensity that you will call the photospeed, just to give you a feeling of the iron is deep. So how does this look like? Well, it very strongly depends on viewing angle. So if you're seeing the flat pancake in this phase, the object is not very bright, but if you see the pancake facing towards you, it's very, very bright. So you can see you get large range of variations. So what I actually find really interesting as a function of angle is whether or not the material is moving towards you or away from you. Because you get strong, what we see is a strong blue shift or red shift of the lines. Okay? Now that may make the determination of the distance more difficult, but in principle, it's a very nice characteristic that if the material is moving away from you or towards you, you clearly see it in the spectrum. These broad peak sigma profiles are really beautiful indicators of the velocity. Oh, this is what I wanted to show. So then, I just wanted to. This is the specific energy per unit mass. Without burning, you get a fairly symmetric shape. We're about half and half, and of course, once you inject the burning, you get more material on that. Again, the energy required to tear this white dwarf apart is supplied at the expense of the orbital kinetic energy, which is larger in this case by 300 times the binding energy of the white dwarf. And then, not only you're going to have these weird supernova, but what's going to happen when they fall back into the intrinsic mass black hole. So what I'm going to show you, a movie is what happens, of the swallowing of the bound debris. Maybe I'll play it first, and then I'll show you the features. So the star basically gets ripped apart. You have about half here in this case. You get about 60–70% of the energy that is bound. 30% it starts falling back. Yeah. The way that you should think about it, the thing that matters is the depth at which the star goes into. Yeah? The most bound material goes into this, elliptical orbit with a smaller semi-major axis, and you start spreading the semi-major axis. So what you get here, you get an angular momentum redistribution shock, yeah? And then you get a nozzle. Why? Because the size of the orbit compared to the tidal radius is much larger. So a lot of the orbits are concentrated here. And as you can see, what you're looking at here is the circularization of the material to ultimately form an accretion disk that's twice the tidal radius. Yeah? Now, should you believe anything that what you're seeing? The answer is probably not, because we're using an adiabatic equation of state. All of the pressure is radiation pressure dominated. As I will show you, the black hole actually accretes at about 10⁷ times the Eddington limit. Yeah. So as you know, going from n thought to a luminosity is tricky.
This is the power for mass.
Yes. So yeah, as I was showing you, the two things, and this also happens in massive stars, and we have done the simulations to try to understand the circularization process. Actually, the energy that you radiate here, it's not very important. The other thing that you should think about, for example, is that the tidal radius for a solar mass type star, it's about an AU. And if you put one solar mass of material and spread it, it only becomes optically thin at 10⁻⁵ centimeters. Yeah? So in this process of re-randomizing the energy and angular momentum to form a disk, if there's any amount of mass that actually goes into a radiation-supported envelope, you will become optically thin. Yeah? So it's very difficult to, in principle, predict the observation signatures. You see both the nozzle and the angular momentum redistribution shock. I won't play this again. Or if you want, you can watch it. The point that I want to make is that the mass supply is above the Eddington rate for as long as a year. And after a year, you go below the Eddington rate. And of course, at the Eddington rate, the sort of live body temperature is about 0.1 K. So in principle, if this object is radiated in the X-rays, and you should keep in mind all the caveats about opacity and radiation pressure, you can, in principle, if you see one of these weird transients, you say, go back to Chandra, even a year after, and you can see the X-ray source. That would be, although not very luminous, if you have a targeted observation. Okay, so just to finish, what we find is that for most favorable cases, beta 4 gives you a nice shock development. Of course, that depends on the mass of the white dwarf and whether it's carbon, oxygen, and helium, because the ability to actually ignite either of these different. So you get a faint thermonuclear explosion. And just for a galaxy, say, for example, harboring 100 intermediate mass black holes, if you believe that every solar cluster has an intermediate mass black hole, then you expect the rate to be, say, 7,000 times smaller than a timeline. So I would view this as a highly optimistic, very highly optimistic estimate, but the only thing I want to point to you is that LSST, for example, is going to find 300,000 timelines. So finding a few of these odd balls is not really in the realm of being extremely unlikely. The nice thing is if you find something interesting in the spectrum, then you may want to go back and look at what are the observational signatures of the accretion. And if you're able to, as I know Linda's coming here, some of the nice models that Linda has, if you actually are able to effectively eject the wave that is relativistic, in which the thermal energy doesn't actually get depleted, you may see these being really relatively bright. It's very difficult unless you have an exit-like object to find this in an all-sky inference. So just to finish, these are sort of the observational signatures rundown that people discuss the gravitational waves, which of course last for the duration of encounter. These, which also may not longer exist, the principal CITA. We talked a little bit about this shock breakout, which lasts tens of seconds, and the peak out was about 10 to the 43 ergs per second for about a minute. We have calculated recombination optical transients from these systems, which give you 10 to the 39 to 10 to the 43. These recombination transients, I didn't have time to talk, but they're beautiful because it depends totally on the mass of the star. Because that tells you how much recombination energy you have. So if the star is rather massive, say the iron mass around these supermassive black hole is top heavy and most of the stars that get disrupted are massive, then you can get to supernova-like optical recombination lines. Because the energy stored in the recombination is pretty high. So LS star and stars can see this. We talked a little bit about this tidally induced supernova, which lasts weeks. So it peaks at early times, I did emphasize that, but it peaks at relatively earlier times than normal Taiwanese because the diffusion perpendicular is much faster. But they could be very bright, but I would say the average one may be before this magnitude than we have Taiwanese. And then I didn't talk about the fallback, but then there's the fallback expected, which happens, for example, for a 10 to the 6 solar mass black hole in the scale of months, and that is limited by the X, which is factor 44 ergs per second. Something that we're trying to implement is the post-Newtonian corrections to the orbit. When immediately you see these, then things are much more interesting in GR. Now, it never happens that actually the front of the star collides with the back of the star, as basically they cross the orbit. And of course, that depends on the inclination and whether or not during the orbital plane. These are, of course, with the Schwarzschild metric. But what we're doing is now including the post-Newtonian corrections to the orbit. Part of what I'm doing right now is an API to work with Ruiz and trying to do this with full GR. Include, of course, orbital energy losses by gravitational waves in a better approximation than we do. A more realistic equation of state, and we hopefully want to understand the treatment of the atmosphere. And unfortunately for that, you have to do 1D models and see how the atmosphere is collapsed rather than using these cells that were on top of it. Thank you.
Time for questions.
So you mentioned that the tidal supernova was on average 2 orders of magnitude different than regular tidal magnitude. Why is that?
Sorry, 2 magnitudes.
2 magnitudes. Okay, so not so like why is it dimmer? Do you use less time?
Less nickel.
Less nickel.
So you gain in luminosity because you diffuse early. So your luminosity is slightly brighter even though it's less. So you have to be careful not to get your cadence wave time scale, like 2 days time scale, as LSST and PPM are doing with time. And yeah, what I'm quoting this for a 0.6 carbon on it.
I guess you take a lower than
Yeah, you just get more. And they don't quite fit the
That's good.
So for the late north cases, you put up the rates at the end. How do you determine them? Because now you're talking about, are you using clusters or how many white dwarfs?
I can give you 2 rates. So one rate is, the most optimistic one is to use smaller clusters because you have 100 per galaxy, and the densities are not that different. stellar density number. So that would hit.
You assume everyone has it.
And then you assume, well, depending on what you're putting on, an average of 100 dollars. Now, you can do the following, which is a little bit more dangerous, and is extrapolate that mass function that I showed you, lower masses, and assume those stars are abundant enough that you can get some rate that is effective. And in that case, you may be at a factor of 10 or 50, right? All now, in that case, it's much more difficult to go to very low luminosity dwarf galaxies and still think that you don't need some effective. But I'm kind of interested that in the realm of 10 to the 5, 10 to the 5.5, 10 to the 4.5, in that range where you still may expect some of these dwarf galaxies to contain black holes or something like omega Cent type of course, then white dwarf will be effectively disrupted. But yeah, I agree with you that that may be a stretch.
I mean, so even if those rates are too small, then you don't expect there are obviously
Not
electrons, but they're way too.
So there's two claims which are interesting of remnant-like features that people are seeing associated with globular clusters. Sort of shock detect that. And Jimmy Irwin, I think from University of Michigan, did a thesis of this system, which actually has abundance similar to a type 1A and it's in a globular cluster. The interaction of the stellar winds of the globular cluster will detect that will give you something along the lines. That's the only.
Well, Enrico's going to be here tomorrow morning, so if you want to talk to him.